Hello, everyone. This is Sihan Liu bringing you testing closeness of multivariate distributions via Ramsey theory. This is a joint work with Elias Diakonikoulos and Daniel Kane. Let's first review the standard definition of closeness testing, or the so-called two-sample hypothesis testing problem from the hypothesis testing literature. Let PQ be two unknown distributions. Given sample access to them, our goal is to distinguish between the case that P is the same as Q versus that P and Q are far from each other. Under this general formulation, a lot of different statistical tests have been proposed, each applicable in some different setting. But before we dive into the details of these tests, we need to be more explicit about what we mean by far here. In the distribution testing literature, the most common distance measure is a total variation distance, defined as the maximum discrepancy between the probabilities of any event under the two distributions. This is a natural statistics, as if two distributions are close under TV distance, then any event must happen with about the same probability under the two distributions, and therefore we can pretty much treat the two distributions as the same. A line of work has characterized the sample complexity of closest testing under TV distance for discrete distribution. In particular, when the distributions are supported on a domain of size n to the power of 2/3 many samples are asymptotically sufficient and necessary for the problem. However, the approach cannot be easily extended to continuous distributions. Indeed, testing under TV distance becomes obviously impossible, as continuous distributions can be used to simulate discrete distribution with arbitrarily large domain size. In other words, one would need essentially infinite many samples for the test in the worst case. A reasonable relaxation is to make the distance metric less stringent. A common one is the so-called Kolmogorov distance. The distance can be defined between any pair of one-dimensional distributions and correspond to the maximum pointwise discrepancy between the cumulative density function of the two distributions. The corresponding test statistic, which is known as Kolmogorov-Smirnov test, simply computes this quantity between the empirical distributions defined by sufficiently many samples collected from the unknown target distribution. Let's briefly reflect over the two distance metrics we have considered so far. Total variation distance is a powerful distance metric, but no sample-efficient tester could possibly exist. On the other hand, testing under Kolmogorov distance requires much fewer samples, but the distance metric can be too weak for even well-behaved distribution family. In particular, even for one Gaussian distribution, they could differ significantly in parameter distance, but are still close under Kolmogorov distance. Naturally, one would hope for a distance metric that interpolates between the two extremes. The AK metric, which had been studying in the prior work, can be viewed exactly as such a candidate metric. In more detail, the 1D AK distance is defined as the maximum discrepancy witnessed by any k disjoint intervals. When k equals to 1, we recover the definition of Kolmogorov distance. When k approaches infinity, AK distance converges to the TV distance under mild assumptions on the underlying distributions. The task of testing whether an unknown distribution is close to a known one under the AK metric, known as the AK identity testing, has been proposed and resolved by Diakonikoulos, Kane, and Nixon in 2014. Subsequently, the same set of authors generalizes the problem to closest testing between two unknown distributions. Surprisingly, the optimal sample complexity has been shown to be k to the power of 4/5, which is notably different from what one sees in closest testing of discrete distribution. Interestingly, as a byproduct of AK testing, one also obtained optimal TV disk testers for structured distribution families, including mixture of Gaussian, monotonic, and log concave distributions. Each of these tests correspond to some AK tester with an appropriately chosen K. The next question is then, how do we generalize this distance metric to multivariate distributions? Perhaps the most straightforward generalization is to replace intervals by axis-aligned rectangles. This gives rise to the definition of multivariate AK distance, where we compute the maximum discrepancy captured by any k disjoint axis-aligned rectangles between a pair of target distributions. Notably, this definition has been considered in the context of learning and identity testing in prior literature. Specifically, for identity testing, it has been shown that multivariate AK testing essentially has about the same complexity as its 1D counterpart up to some polylogarithmic factors. Multivariate AK closeness testing, which is the main focus of this work, turns out to be very different from its 1D counterpart. On the positive side, for any constant d, we show that there is an algorithm with sample complexity k to the power of 6/7 times poly 1 over epsilon times some polylogarithmic factors. On the negative side, even for d dimension equals to 2, we show that k to the power of 6/7 times poly 1 over epsilon many samples are necessary for this test. This is notably worse than the sample complexity of 1D AK closeness testing. To interpret the results, let's examine how the dependency on k evolves as d increases. When d equals to 1, where in the case of 1D AK testing, and the sample complexity has been characterized by the prior work to be k to the power of 4/5. When d equals to 2, the sample complexity suddenly jumps to k to the power of 6/7. However, as d further increases, the exponent on k just stays at 6/7. Quite surprisingly, unlike identity testing, this suggests that the sample complexity of AK closest testing has gone through a sharp phase transition from the single variate to the multivariate setting. This is the main conceptual message of our work. While the above settle the dependency on K for constant epsilon and D, a complete characterization of the sample complexity in all relevant parameters remains open. For the log DK terms, we note that it has also appeared in the sample complexity of multivariate identity testing. So in that sense, this term should be expected. The poly D epsilon term is more problematic. Though we conjecture that it should be some fixed polynomial independent of D, our current analysis technique fails to get us there. This is therefore left as the major open question for future work. In the remaining of the talk, for ease of presentation, we'll assume that D and epsilon are some absolute constant and focus on the dependency on K. We'll next discuss important technical ideas in the proof of the upper bound. As our starting point, we remark that if the witness rectangles are known a priori, then the problem simply reduces to closest testing over discrete domains. And by an application of the prior closest testing for discrete distribution, we know k to the power of 2/3 many samples is sufficient. The key technical challenge is therefore whether we can identify rectangles that capture enough discrepancy between the two unknown distributions. An important lesson from 1D AK testing is the following. One should not hope an obliviously chosen set of rectangles to suffice for the purpose. In particular, it was noted in DKN15 that even for 1D AK closest testing, any obliviously chosen set of intervals may capture no discrepancy when the pair of adversarially chosen distributions have large AK distance. Therefore, it is necessary for us to consider rectangles defined by the sample. In particular, given two sample points, we consider the rectangles made up of all points whose coordinates are sandwiched between the coordinates of the given point. The main intuition for using such a rectangle is the following. Let R be a rectangle that captures non-trivial discrepancy between the pair of unknown distributions. Under some wishful thinking, If a pair of points happen to fall in R, the rectangle defined is likely to capture a non-trivial fraction of the parent rectangle R in expectation. Under some wishful thinking, this suggests that the rectangle is also likely to capture a non-trivial fraction of the discrepancy within R as well. Surprisingly, this optimistic intuition turns out to be true and can be shown via tools from Ramsey theory. But before we dive into the proof of this result about discrepancy captured by random rectangles, we briefly sketch how one would leverage this structural property to devise an efficient tester. Without loss of generality, we can assume that there exists k unknown rectangle such that each of them has mass about 1 over k and witness about epsilon over k discrepancy between the two unknown distributions. If we take m samples, approximately m squared over k many such rectangles will contain two sample points. Therefore, by the structural result, we know the subrectangles defined by the point pair contained will help us capture a non-trivial fraction of discrepancy, which is about m squared over k squared times some constant depending on d and epsilon. An issue is that we only know the existence of such subrectangles defined by sample points, but cannot easily identify them, because we do not know the R1 to RK rectangles a priori. Fortunately, this can be solved via a technique developed in the prior work of multivariate identity testing under AK metric. This is called rectangle grid covering. In particular, the techniques allow us to construct a cover for all possible rectangles that can be defined by the sample points, and transform the original distribution P and Q into discrete distributions supported on this cover. Moreover, the discrepancy of the transformed distribution will be supported on about m squared over k many domain elements and comparable to the discrepancy captured by the bat set of disjoint rectangles defined by the sample points. With this technique in our hand, the problem becomes essentially the same as L1 closest testing for discrete distributions, which can be solved with standard techniques for closest testing of discrete distributions. Balancing the number of samples used to search for discrepancy witness rectangles and the final testing procedure then gives a sample complexity of k to the power of 6, 7. We now sketch the proof of the key random rectangle discrepancy lemma. Before showing that this rectangle captures enough discrepancy, as a prior condition, we'll show that the rectangle given by a random pair of points is at least capable of capturing a non-trivial fraction of the mass of the distribution they're sampled from. Surprisingly, the proof boils down to a statement in Ramsey theory about monotonically increasing subsequence among distinct real numbers. To make the connection, we'll need slightly rewrite the expected mass capture. In particular, the probability mass of a rectangle is precisely equal to the probability of the event that a third point z, sampled independently from the distribution, happens to lie within the rectangle. So how can we bound this probability? If one tries to construct discrete distribution to minimize this quantity, one will find out this is essentially equivalent as asking, how many distinct points can one put in a d-dimensional space such that no point is captured by the others? This turned out to be a classical result shown by de Bruijn, which served as a high-dimensional generalization of the famous Erdős-Sacras theorem. In particular, de Bruijn shows that one can embed at most n equals to 2 to the 2 to the power of b minus 1 many points in the space satisfying this condition, and one cannot add more points on it. We can then leverage the result to derive a lower bound on the probability of our concern. Note that to draw 3 samples from a distribution is equivalent as that one first draw sample set S consists of an independent sample from the distribution, and then select 3 distinct points from the sample set S. By de Bruijn's theorem, there must exist a triplet XYZ such that Z is included by the rectangles formed by XY. Note that this triplet is selected with probability at least 1 over n cubic, and this holds for any sample set F. Therefore, the overall probability is then lower bounded by 1 over n cubic as well, which is some function depends only on D. Now, we know that the rectangle defined by two random points are capable of collecting enough mass. We can then strengthen it into a proposition concerning the discrepancy collected by rectangles. Let R be a rectangle that collects absolute fraction of discrepancy between a two distribution. After normalized by the mass of the rectangle, we'll show that two random points sampled from the mixture distribution condition on this rectangle defines a subrectangle that collects a non-trivial fraction of the discrepancy. What we have just seen shows that the rectangle defined will collect a non-trivial fraction of the mass of the parent rectangle R in expectation. Therefore, if the discrepancy within the subrectangle is at least absolute fraction of its mass, we're done. Otherwise, we can look at the remaining space and carve it into at most OD many other subrectangles. If we consider the discrepancy density, namely the amount of discrepancy divided by the mass, we know that at least one of the rectangle must have a higher discrepancy density compared to the parent rectangle. This is because RXY already has a lower discrepancy density. We can therefore zoom into the subrectangle with higher discrepancy density, conditional on the event that the two random points are sampled from this subrectangle, and restart the process. As the discrepancy density approaches 1, the situation qualitatively starts to resemble the case that only one of P and Q assigns non-zero mass to the rectangular region. In that case, we note that collecting enough mass is equivalent as collecting enough discrepancy. And this concludes the proof of the proposition. This concludes the talk, and thank you for your time.